So, continuing this idea of curve sketching, and that last video came to 37 minutes or something. Not really surprising because, well, I mentioned by the end of the video how many connections any of these questions require to someone to make, and I don't know if this is going to be any different. So let's see. Let's get started. I want to start by something called L'Hôpital's rule, or it looks like L'Hospital's rule. And to understand how to use this, it's probably easiest if I actually start at the bottom here. And so in general, in certain cases, in a lot of cases, if you want to find the limit of something divided by something else, really, if you want to find the limit of some sort of fraction, quite often that limit is actually the same if you find the limit of the derivative of the numerator divided by the derivative of the denominator. And quite often it's actually easier to directly find the limit of this as opposed to this. And these will be the same. The derivative of some fraction will be equivalent to the the limit as we approach some number of some fraction will be the same, will be equivalent to the limit of that as we approach that same value of the derivative of the numerator and the derivative of the denominator separately, as long as what we have up here is true. And so as long as the limit of the numerator and the denominator both approach 0, or the limit of the numerator and the denominator both approach plus or minus infinity. So if that's the case, which quite often it is, very often it is, then you can find the limit as we approach some value using this. And to be honest, the vast majority of limits we looked at in the unit on limits, we could have used this rule. That's it. At the time we didn't know about derivatives. But again, it's quite helpful. And this comes into play with curve sketching because quite often as we approach, quite often it's helpful to think about the limit of a function as we approach positive or negative infinity, because that lets us figure out where the if there's any horizontal asymptotes. So before we get into the curve sketching side, let's just practice this using this rule a bit. And for example, for this first one here, before I actually use L'Hôpital's rule, I'm going to just check and make sure we can, and really to explain those little conditions we have at the beginning. So to check, so let's just check. When x equals -2, let's check what x cubed plus 8 equals. And when x equals -2, x cubed plus 8 equals 0. And when x equals -2, let's check the denominator. X plus 2 equals 0. And so as x approaches -2, the numerator and the denominator both approach 0. Well, that's what's kind of stated right here. Right? If the limit of the numerator and the denominator approach 0, both of them, then we can use this rule. And so now I can use L'Hôpital's rule, which means to find this limit, instead of doing anything that we did earlier in the course, quite often we use the conjugate or we factored or there's a whole bunch of things. I'm just going to find the derivative of the numerator. I'm not going to use the quotient rule. I'm not finding the derivative of the entire function. I'm just going to find just the derivative of the numerator, which is 3x squared, and just the derivative of the denominator, which is 1. Now that's not my limit, but now if I want to find the limit as x approaches -2, of this right here, I can just find the limit as x approaches -2 of this, which is much more convenient because I can just substitute x with -2. And so I can see this is going to equal 3 times -2 squared, which is 12. And so again, we can't always use this rule. We can only use this rule when, like in the previous case, both the numerator and the denominator approach 0, or both the numerator and the denominator approach plus or minus infinity. Okay, so with that said, well, you should always kind of check. All the rest of these will work for that. So let me just get straight into the rule. But for example here, if I want to find the limit as x approaches 0 of tan 3x over sine 2x, let me first differentiate the numerator. And if you use the chain rule, so I get secant squared 3x times 3 divided by the derivative of the denominator. Again, use the chain rule, which is cos 2x, all times 2. Oh no, just got a warning about my pencil, my Apple Pencil. Let's hope it makes it through the video. Let's see. And with that said, that means the limit as x approaches 0 of the expression at the top must be the same as this. And again here, there's nothing stopping me from just evaluating as x approaches 0. And I know that with a little bit of work, especially if I kind of clean this up a bit. For example, I can rewrite this as 3 over 2 times the cos of 2x times the cos of 3x squared. Right? Secant same as 1 over cos. And now I'm literally going to substitute all these x's with 0. So I have 2 times the cos of 0 times the cos of 0 all cubed. Well, the cosine of 0 is 1. And so in the end, I have 3 over 2. OK, let's get going for my pencil dice. Ooh, this is exciting. Let's try these ones. All right, so same idea. Differentiate the top, differentiate the bottom. The numerator is 1 plus 2x. The denominator is negative 4x. And so now I want to find the limit as x approaches infinity here. That's it, as x approaches infinity. I can't substitute x directly with infinity, but I can, we've learned how to do this earlier in the course. For example, let's say I could break this up into I could take out a factor of x from the numerator and 1 over x plus 2. And then I have x in the denominator. Those cancel out. And now I can see as x approaches infinity, remember from earlier on in the course, expressions like that go to 0. Oh, sorry, there's a 4 in the denominator. Come back there, 4. Cancel out the x, but there should be a 4 right there. There we go. And so this is 0 plus 2 over negative 4, or negative 1/2. And lastly, one more example of just focusing on using this rule, again with limits as we approach infinity. Let's look right here. Differentiate the top using the chain rule. I get 1 over root x times the derivative of root x, which is 1 over 2 root x. All over the derivative of the denominator. That's it. I can clean this up, definitely. And so my numerator, for example, is 1 over root x times 2 root x, which is 1 over 2x, all divided by 2x, which is the same as 1 over 4x. And now find the limit as x approaches infinity of this. Again, as x gets infinitely large, this whole expression gets closer and closer to 0, and so this must equal 0. And so there's a decent chance, especially with limits towards infinity, we may have to review some things going back to Unit 2. But in general, this is always an option for finding limits, and quite often it's a faster option in terms of trying to find these asymptotes. So with that said, let's get to it. So what I have here, and I'm going to go through 2 examples, are just essentially, I want to sketch this function. I want to sketch 2x squared over x squared minus 1 using what we know about derivatives. Okay, and this particular example, I've given you the first and second derivative already, although we should be able to find those if we needed to on our own. The first derivative, we could use the chain rule. Second derivative, we do the same thing for the first derivative, using the chain rule and the, sorry, I said chain rule. You will use a chain rule, most likely, but I actually meant to say quotient rule. But that said, the actual process of going from here to here, or from here to here, is the sort of thing we focused on in the last unit. It's very, very important, but for time reasons, I'm not going to show you all that. And to be honest, sometimes on an assessment, I may just give you these derivatives to see if we know how to use them. Okay. Now, with that said, looking up here, please don't think of these as like step 1, step 2, step 3, step 4, step 5, step 6, step 7, 8, 9, whatever. You could approach it that way. These are just things that are helpful to look for. We don't want to be rigid in our thinking and thinking we have to do one after the next. And as it says, it may not always be possible or reasonable to determine every of these points below. The more we can figure out, the more information we have, and the more then we can start to visualize what this graph must look like. Okay, the first thing I want to do, though, is I want to find the domain. I always recommend trying to find the domain right away. In this case, the domain is rather straightforward. I can just see by inspection the domain must be x cannot equal plus or minus 1, because then it'd be dividing by 0. So I know right away this function does not have a domain of all real numbers. It has some sort of discontinuities at plus or minus -1. That's it. I don't know yet the type of discontinuities, but I'll just leave it at that for now. Okay, next, I'm going to find the x and y intercepts. I don't need calculus for this. Find the x-intercepts. Make y equal 0. And so I get 0 equals 2x squared over x squared minus 1. And solve this algebraically. And remember, anytime you want to find the x-intercept for any function or relation, make x equal to 0, solve for y. In this case, you get, if you solve, you get x equals 0. One x-intercept. Now let's find the y-intercepts. Usually easier. If you want to find the y-intercepts, you want to make x equal to 0. So usually easier. If we're dealing with functions, they're almost always easier because it's usually set up to solve for y. Replace y with 0, you get, replace x with 0, you get y also equaling 0. So I know there's just one x and y intercept, and it's the same value, both at 0. So this function goes to the origin. All right. Another thing that's helpful is to kind of determine if the function is even or odd. And again, this goes back to the beginnings of the course. So if I go back to 2x squared over x squared minus 1, I know this function is even. How do I know it's even? Because if I take x and replace it with negative x, I get an equivalent equation. And if you review back what it means if a function is even, visually that means if you reflect it horizontally, it looks the same. And so algebraically, that means if you perform a horizontal reflection, you replace x with negative x, algebraically the two graphs should be equivalent. And I can see that here because all my x's are being squared, so when they're negative, it's still the exact same thing. So I know my function is even. Which means, again, it is symmetrical about the y-axis. All right. Again, I still haven't actually done anything that requires any derivatives yet. Haven't even used the first derivative yet. Well, now I want to see if there's any asymptotes. And if there's any asymptotes, I need to find the limit as x approaches plus or minus infinity. Now in this case, I know if there's going to be a limit that converges on some number, it's going to be the same for plus and minus infinity, because looking at the equation, x is always squared, so whether we're approaching positive or negative numbers, I know it's going to be the same. Plus I know the function is even. Okay, so I'm just going to find the limit. I'm going to go directly as x approaches plus or minus infinity of 2x squared over x squared minus 1. Well, this is a great example of where we can use that L'Hopital's rule. And so while I could figure this out directly, might as well differentiate the numerator and the denominator. It will make it a simpler expression. So I can think of instead about the limit as x approaches plus or minus infinity of 4x over 2x. Well, cancel my x's out. I can see this must equal 2. So I know there is a horizontal asymptote when y equals 2. And I know not only that, I know the function approaches it both forever to the left and to the right. So step by step, I'm figuring out a whole bunch of characteristics about this function. Okay, next, I want to find out where my function is increasing or decreasing. And for that, I need to focus on my first derivative. And my first derivative, again, I gave you, but you could use the quotient rule to figure it out. All right. Negative 4x. Okay, so I need to find my critical points. And so I need to think, where is dy dx equal to 0, and where is dy dx undefined, or where does it not exist? So it's going to equal to 0 when my numerator is equal to 0, when x equals 0. That's the only critical point like that. However, I have another critical point, or points, when my derivative does not exist, and that's when I'm dividing by 0. And that's when x is plus or minus 1. So there's 3 critical numbers, or 3 critical points for this function: 0, 1, and negative 1. So and that's it. So I now need to think about, okay, in between those critical numbers, is the function increasing or decreasing? So let me have a little number line. And again, unless there's any other critical points I've missed, which the derivative is not that complex, so there aren't any, then I know everywhere less than negative 1, it's either increasing or decreasing. And same thing between negative 1 and 0. As well, though, don't forget what I've learned before. I know at negative 1, dy dx does not exist. But as well, if I look back at the beginning of the first thing we did, the domain does not include plus or minus negative 1, because I'm dividing by 0 there. So not only do I know the derivative does not exist here, I know there's a discontinuity here. Same thing for 1. Really, that's why the derivative does not exist there, because the function is discontinuous there. However, at 0, I know this is where dy dx equaled 0. OK, so now pick a number less than negative 1, put it into the derivative, see if it's positive or negative. For example, I would pick, I don't know, negative 2. If I put negative 2 into the derivative, my denominator will be positive. So negative times a negative is a positive. In the denominator, no matter what I do, it's going to be positive, because in the end I'm squaring everything. And so when x is negative 2, my derivative is positive, which means my function is increasing in that region. And notice it shouldn't take me long to do the same thing for all the rest. Pick a value between negative 1 and 0, and so on. And so I should get it decreasing. Oh, sorry, it's still increasing right here. It should be decreasing right here, and then decreasing. And so now I know that this 0, where the derivative is 0, I know the function is increasing on one side and then decreasing. So I know this must be a local max. It might be the absolute max, but I know it's a local max. All right, let's see if there's any inflection points. Let's learn about concavity. And so for that, let's look at the second derivative, which again I gave you. And so if there's going to be an inflection point, it's going to be where the numerator, because the whole thing will equal 0. Well, that numerator will never equal 0. 12x squared plus 4x will never equal 0. Oh, sorry, not 4x plus 4. That's what it should be. If there was an x there, it could equal 0. But yeah, it was 12x squared plus 4. That will never equal 0. So that means there's no inflection points. However, if there's no inflection points, that means there's no point where the function changes from concave down to concave up, or concave up to concave down. But concavity still might change at those discontinuities. If concavity is going to change, it's going to be at those discontinuities. That's, again, a discontinuity is not a point. And so there's still, again, it might change concavity, but there's definitely just no point where it changes. And so I'll make a little note about that. And so, with that said, that means if I want to think about concavity, I need to make a little number line here. The only numbers that really matter to me are -1 and +1. If concavity is going to change anywhere, it's going to be at those discontinuities. which again are almost certainly vertical asymptotes. And we can kind of figure that out just from, really, I can just, from the very beginning, I gave you a rational function, 2x squared over x squared minus 1. And so again, if we think back to rational functions, it's probably not surprising this is going to lead to vertical asymptotes. But with that said, let's just check. And so again, pick a number less than -1, -2, put into my derivative, my second derivative. And when I put -2 into my second derivative, come back here, the numerator is positive. And because I'm squaring x, the denominator is always going to be positive. Actually, it won't always be positive because I'm cubing everything in the end. But when x is -2, I have -2 squared, which is 4. 4 minus 1 is 3. Everything's going to be positive. And so when x is less than -1, this is concave up. Do the same thing for the other intervals. You'll find it's actually concave down between -1 and 1, which means concavity did change between those discontinuities. Pick a number greater than 1, and it'll be concave up again. Okay, there's a lot of things we've now figured out. And so at this point, let's sketch this function. And again, at this point, with all this information, it's no different than things we've done earlier, where you have a whole bunch of characteristics about a function, and we kind of step-by-step piece it together. At this point, I would highly recommend you just pause the video before I show what this looks like and just try it on your own. But let me start drawing. And so what do I know? I know I know it goes through 0, 0. X and y intercepts are right there. So I know it goes to that point. I know -1 and 1 are discontinuities. I know it's increasing here. It's increasing here. It's decreasing. It's decreasing. And I know it's concave up. In this region, concave down here, concave up. And I know about these asymptotes. I know about a whole bunch of things. So in the end, without just repeating myself from previous sort of lessons, maybe I'll draw the horizontal asymptote right now, which is at 2. And so I kind of know it has to look something like, I know there has to be a vertical asymptote now here. There's a few ways. Even without remembering some things from pre-calc 12, I know it's increasing here and increasing here. Which means, and it also approaches this infinity, so I can this asymptote, so I know it must have to look something like this. And I know it also has to reach this point right here. Keep in mind, if it went like this, it'd be decreasing. Again, when you start to piece together all these things, we have very few options. So let me draw that side. So it has to look something like this. It must look something like this. Oops. With that said, I also know the function is even, so I can just kind of copy this. I know it's symmetrical. Now at this point, if I hadn't already done all this, I would look at all the points and just double check all things. It means a lot of things here. Notice the concavity is concave up, less than -1, greater than 1. It's concave down in between. My increasing and decreasing intervals all match up. The asymptotes match up. It's symmetrical. I got my x-intercepts, the domain. Everything kind of comes together back to this. And so let's try one more. Now again, you could try this completely on your own, but chances are you may be better off just watching me get everything set up before I draw it. That's it. Sketch a graph of this. I don't give you any other derivatives. So what I want to do first is find the domain. And I can just see by looking at it, the domain is all real numbers. Exponential function has a domain of all real numbers. A quadratic function has a domain of all real numbers. Multiply those together. It's still going to be a domain of all real numbers. So let's find the x-intercepts. So make y equal to 0. Well, the only time this whole thing's going to equal 0 is if this factor right here equals 0. Because e to the power of x will never equal 0, which means x must equal plus or minus √3. Let's find y-intercepts. Which I said is usually easier. In this case, just substitute x with 0, and I can see this is all going to equal -3. Remember, e to the power of 0 is 1, not 0. So 2x intercepts 1 y-intercept. All right, let's find my limits as x approaches plus or minus infinity. This time, and as well, I can just see by looking at the equation, it's not going to be even or odd. You know, just this is an even function, but I multiply by an exponential function, and an exponential function, you know, grows like this. It's not going to be even or odd. If I'm not sure, I could replace x with negative x and see if I get the same thing, and go do this something similar for odd. But I can just tell quickly it's not going to be. That's it. That means I want to find my limits separately. I want to find the limit as x approaches negative infinity. I want to find the limit as x approaches positive infinity. Okay. So all this I'm going to kind of essentially do by inspection. I can't use L'Hopital's rule here because I don't have this rational, I don't have a quotient here. But as x approaches negative infinity, I know that e to the power of x is going to approach 0. And that's just knowing what e to the power of x looks like. E to the power of x looks like this. So as x, if we go farther and farther this way, I get closer and closer, infinitely close to that asymptote, which means I'm getting infinitely close to 0. So it's 0, something getting infinitely close to 0 times a large number. But again, this gets infinitely close to 0, so I can just see by inspection, this must equal 0. As we approach positive infinity, this gets infinitely large, and so does this. And so it just gets infinitely large numbers multiplied to each other, get even more infinitely large. So this is going to approach infinity. So this is all by inspection. All right, now let's find out where it's increasing or decreasing, which means I need to find my derivatives for my first derivative. So going back to my original function, if I want to start finding my derivative, I need to use the product rule. And so I have e to the power of x times a quadratic function. So using the product rule, I get this. All right, so while that's OK, I can clean this up fairly easily by taking out that common factor of e to the power of x from both those. And I get e to the power of x times x squared plus 2x minus 3, which I have this nice trinomial there. If I can factor it, it'll be helpful for what I'm going to do in a moment. And I can factor that. And so that factors x plus 3 and x minus 1. So in terms of finding my critical points, I can see they must be at 1 and negative 3 only. Again, the factor of e to the power of x, that'll never equal 0. And so I know there's only 2 critical points. So I know x equals negative 3 and 1 are my critical numbers. And those are the only ones. Again, this derivative will always be defined. If I look at it, it's very similar to the first function we had. So there's no other critical points. This derivative will always be defined. And so let's draw these intervals. The only numbers that really matter to me are the negative 3 and the 1. Again, pick values for x that are less than negative 3. Again, I'll do one example, negative 4. This will always be positive. Again, everything I'm talking about e to the power of x, go back to my knowledge of exponential functions. That's always going to be positive. When x is negative 4, this is going to be negative. When x is negative 4, this is going to be negative. A positive times a negative is a positive, so I know this is increasing in that interval. Do something similar for the rest. I'll find it's decreasing here, and then it's increasing again right here. So I now know this must be a local max. This must be a local min, because I'm looking at where it's increasing and decreasing. And remember, each of these are where my derivative equals 0. So it's not going to be, it's not going to be a cusp or anything. It's going to be something like, I can actually visualize it quite well. It's going to look something like I had, something like that, because the derivative was actually 0 there. OK, that said, I've already know a lot now. If I can work with the second derivative, I can figure out if there's inflection points. So let's find the second derivative, which is going to get a bit more messy. So I want to take, and I could differentiate any of these right here. I like this one right here the best to differentiate. It's going to be very similar to this using the product rule like we did to find the first derivative. And so if I differentiate that form right there, I start with this. And again, that's using the product rule. And again, like I did when finding the first derivative, I mean, that's fine what I have, but it's pretty easy for me to take out a factor of e to the power of x and kind of write the rest as a trinomial. And I get x squared plus 4x plus 1. And again, what I have right there is comparable to what I had up here highlighted in blue. Right, I took those. When I pulled out e to the power of x up there, I got that x squared plus 2x minus 3. Now I could factor x squared plus 2x minus 3. I cannot factor this. That doesn't mean there's no inflection points, because again, if there's going to be any inflection points, it's going to be where that factor there, x squared plus 4x plus 1, where that equals 0. If that equals 0 somewhere, I know there's going to be an inflection point. I just can't tell really, really quickly. I can't tell in a few seconds by looking at factors. But maybe I could use the quadratic formula. All right, so with that said, quadratic formula, not difficult, sometimes a bit annoying, but in this case we get x equals minus 4 plus or minus all this good stuff. And again, this is all for me trying to find where I'm trying to find where x squared plus 4x plus 1 equals 0. And because if that's going to equal 0 somewhere, I'm going to have inflection points. And I can see it will equal 0 somewhere, because I can see right here, this is going to be a positive number. If that was a negative number, if that discriminant, it's called, was a negative number, then the quadratic formula would have no solutions, which means this factor would never equal 0, which means this function has no inflection points. But it will, I can see. And so that is not a negative number, so I get negative 4 plus or minus root 20 comes to, over 2, which simplifies to negative 2 plus or minus root 5. Which I will say, if you decimalize it, which is just a little bit helpful for visualizing the graph in the end, I get negative 4.24 approximately, and positive 0.24. That said, more importantly, these are our inflection points. So let's figure out where its concavity. And again, in terms of concavity, all I care about are those two inflection points. I'll write the exact values. So I'll get negative 2 minus root 5 and negative 2 plus root 5. And then pick a number. Now again, this is where the decimals might help. That negative 2 minus root 5 is approximately negative 4. Pick any number less than negative 4. You could go negative 5 or negative whatever you want and put it into the second derivative. A few more calculations to do, but again, really it's all about paying attention to the x squared plus 4x plus 1 part. E to the power of x will always be a positive number. And so, You know, it takes a little bit of time, but we should find that we get a positive value when it's less than this inflection point, so it's concave up right here. It's concave down in between. That's probably the easiest to check. I'd just pick 0, put that into the second derivative, and then concave up again. And again, we have a lot of stuff we figured out. I know where there's inflection points, I know the concavity, I know where it's increasing or decreasing, I know where there's a local max and a local min, I know that it's a derivative of 0 there. I know as we approach infinity from the left, there's a horizontal asymptote at 0. As we go to the right, it just keeps going up forever. I know that there's 2 x-intercepts. I know there's a y-intercept. I know a lot of things. And so sometimes we know so many things it just gets bewildering, which I appreciate. But at this point, definitely I recommend you pause the video before you watch me piece it all together. Look at this, my battery of my pencil has not died yet. So a few things, you know, so you can start with your x and y intercepts. I know there's one at negative root 3. I know there's one at positive root 3. Some of the first stuff we found. I know there's a y-intercept at negative 3. I know it goes through there. I know at negative 1 and where was it? At positive 1 and negative 3, I have some critical points. So positive 1 I'll start with. Positive 1 is a little bit less than root 3. So about right there. So at that point, I have an absolute min when x is positive 1. And at negative 3, so let's say over here, I have an absolute max. I also know I have a horizontal asymptote right on the x-axis. And I know the limit as we approach negative infinity will equal that. I know there's a local max at negative 3, which means I know it must be somewhere above the x-axis, just from looking at what I have here so far. So I don't know, up here somewhere. Now if I want to find the x-coordinate, or sorry, the y-coordinate, I could just plug negative 3 into my original function. And I will say you get about 0.299, because it's above the x-axis. And I knew it had to be, because I knew it had to go through here, and I knew it had to have a max somewhere. And so with that said, I can now visualize the left side of this pretty well. I'll draw this lightly first. I know there's an asymptote here. I know it has to come up like this. And then, you know, there's my quick little sketch. It goes down. OK. That's what I can make adjustments if necessary. I know when x is positive 1, there's a local min, which makes sense from what I'm drawing, because that means, let's say, around here, it's got to go down. And then I know it's got to quickly go back up. It has to have an x-intercept right there. And then it looks like it just keeps going up forever, because I know the limit as we approach infinity is infinity. That's it, my inflection points. You know, I knew at about negative, I knew there's an inflection point at about negative 4.24, so somewhere around here there must be an inflection point. And that matches up with what I've drawn. Notice if I look at that, it's concave up to one side, concave down on the other. So there's an inflection point there. So notice I didn't really need, if I took into account everything else, I didn't really need to figure out that inflection point. But it's confirming what I know. And there's another inflection point we know at about 0.24. So just somewhere around here is another inflection point. Well, that's, again, just confirming what I've already drawn. And because if I look at what I've sketched out here, it is concave up to the left of that first inflection point. It is concave down in between those two, and then concave up again. And since there's no other inflection points, I know this function just keeps going up without, like, it doesn't kind of curl sideways or do something like that, because there would be another inflection point. And so I'm done. Again, I'll never say it's easy. I'll just draw it a little darker. I'll just label that local min down there. I'll label this local max. So again, right get there. That was my local max. And now that I've drawn the entire graph, I can see that it's just a local max. It's not an absolute max. There is no absolute max. That's because it goes up forever. But I now know that this point down here, which is the x-coordinate is 1. The y-coordinate I could figure out by putting 1 back into the original function, which I get about negative 5.43, which I don't really need, but it's not hard to do. I know that is not only a local min now, I know that's an absolute min. Just from looking at the graph, that's the absolute lowest point of the function. And in the end, I was able to kind of use all the many, many, many things I figured out about this. And it looks like this video took a while again. We'll see, only time will tell if it beats 37 minutes. Oh, that's a tough lesson. I bet a lot of you will find this the hardest lesson of the course. Definitely of this unit for a lot of people. But